Kinetics is the branch of chemistry that deals with reaction mechanism and the rate of a chemical reaction. The rate of a chemical reaction is the change in the concentration, that is moles per liter, of a reactant or a product per unit time. Let us consider a simple chemical reaction as shown here. A forms B, that is 1 mole of A reacts to form a mole of B. Here, the rate of disappearance of reactant A equals the decrease in its concentration per unit time, which is minus delta A by delta T, and the rate of appearance of the product B is equal to the increase in its concentration per unit time, which is plus delta B by delta T. Look at the chemical reaction shown here. Here, small a, b, c and d are the stoichiometric coefficients of the reactants A and B and the products C and D. Then the rate of disappearance of the reactant A equals minus delta A by delta T. The rate of disappearance of the reactant B equals minus delta B by delta T. The rate of appearance of the product C equals plus delta C by delta T. And the rate of appearance of the product D equals plus delta D by delta T. The rate of reaction is then given by minus 1 upon A delta A by delta T, which is also equal to minus 1 upon B delta B by delta T, which also equals 1 upon C delta C by delta T, which also equals 1 upon D delta D by delta T. The rate law of mass action states that the rate of a chemical reaction at a given temperature is directly proportional to the product of the concentration of the reactants. Let us consider a chemical reaction as shown here. Here, the reactants are A and B and the products are C and D. The letters small a, b, c and d are the stoichiometric coefficients. Then the rate law of mass action states that the rate of the reaction is directly proportional to the product of concentration of reactant A raised to an exponent x and concentration of reactant B raised to an exponent y. When we remove the proportionality sign, we can introduce a proportionality constant k, which is also known as the rate constant. Then we can write the rate of reaction equals k A raised to x B raised to y. In the previous two sections, we understood how to express the rate of a chemical reaction using two methods. One based on stoichiometry and the other by using the rate law of mass action. Let us now understand what do we mean by the order of a chemical reaction. Let us consider a chemical reaction A plus B forms C plus D. We know that the rate law of mass action states that the rate of a chemical reaction at a given temperature is directly proportional to the product of the concentration of the reactants. So here the reactants are A and B. So hence we can say that using the rate law of mass action, the rate equation will be as follows. Rate equals K multiplied by A raised to x multiplied by B raised to y. Here K is the rate constant of the reaction. A in square brackets is the concentration of the reactant A and B in square brackets is the concentration of reactant B. X and y are the exponents. X is the exponent of the concentration of reactant A and y is exponent of the concentration of reactant B. The exponents x and y indicate how sensitive the rate of the reaction is to the change in concentrations of A and B. The sum of these exponents, that is x plus y, gives us the overall order of a reaction. X and y also represent the order with respect to the reactants A and B respectively. Therefore, order of a reaction is defined as the sum of powers of the concentration of the reactants in the rate law expression. The order of a reaction can be 0, 1, 2, 3 or any other fraction. Hence, in the above case, rate equals K, concentration of A raised to exponent x, B, concentration B raised to exponent y. The order of the reaction is the sum of the exponents, which is x plus y. Note that the order of the reaction with respect to the reactant A is x and the order of the reaction with respect to the reactant B is said to be y, and the order of the overall reaction is x plus y. Let us look at a few examples and look at the expressions of the rate of a reaction and estimate its order. In the first example, the rate is K multiplied by concentration of A whole square multiplied by B. Here, the exponents are 2 and 1. That is, the exponents of the concentration terms are 2 and 1. We know that order is the sum of the pass of concentration of the reactants in the rate law expression. So hence, the order will be 2 plus 1 in the first case, which is equal to 3. In the second example, the rate is defined as K multiplied by concentration of reactant A raised to 0. Now here, the exponent of the concentration of reactant A is 0. Therefore, order, which is the sum of the pass of the concentration of the reactants, is also 0. Hence, it's a 0 order reaction. In the third example, the rate is defined as K multiplied by concentration of A raised to 3 by 2 multiplied by concentration of B. Here, the exponent of concentration of the reactant A is 3 by 2 and the exponent of the concentration of reactant B is 1. Order, which is the sum of the pass of the concentration of the reactants in the rate law expression, here will be 3 by 2 plus 1, which is 5 by 2, that is 2.5. Hence, the order of this reaction, whose rate is given as K A raised to 3 by 2 B, is 2.5. In the second example, we saw that the exponent of the concentration A was 0. This is known as a 0 order reaction. A 0 order reaction means that the rate of the reaction is independent of the concentration of the reactants. Let us now understand what do we mean by molecularity of a reaction. In the previous section, we understood what do we mean by the order of a chemical reaction. Let us now understand the term molecularity of a chemical reaction. The number of reacting species, that is, atoms or ions or molecules, taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction is called a molecularity of reaction. For example, in case a reaction takes place such that only one reacting species is involved, then the reaction would be called a unimolecular reaction. That is, the molecularity of the reaction is equal to 1. A unimolecular reaction is a reaction when only one reacting species is involved. For example, in the decomposition of ammonium nitrate, only one reacting species, that is, ammonium nitrate, is involved. The reaction is NH4NO2, which is ammonium nitrate, forms N2 plus 2H2, that is nitrogen and water. Here, there is only one reacting species involved, hence its molecularity is equal to 1 and it's known as a unimolecular reaction. Similarly, a bimolecular reaction is a reaction which involves simultaneous collision between two reacting species. For example, the dissociation of hydrogen iodide is a bimolecular reaction, that is, its molecularity is equal to 2. Because two molecules of hydrogen iodide must simultaneously collide, only then will it dissociate into hydrogen and iodine. The reaction is 2HI forms H2 plus I2, that is, 2 moles of hydrogen iodide react to form a mole of hydrogen and a mole of iodine. Similarly, a trimolecular reaction is a reaction which involves the simultaneous collision between 3 reacting species. Trimolecular reactions are very rare. Let us take an example. A trimolecular reaction involves 3 reacting species which simultaneously collide. The reaction of nitric oxide with oxygen to form nitrogen dioxide is an example of trimolecular reaction. Here, two molecules of nitric oxide, which is NO, react or collide with one molecule of oxygen O2 to form two molecules of nitrogen dioxide, which is NO2. The reaction is 2NO plus O2 forms 2NO2. That is, the molecularity of this reaction is 3, hence it's called a trimolecular reaction. The probability that more than 3 molecules can collide and react simultaneously is very small. Hence, in reality, the molecularity greater than 3 is not observed. Note that molecularity of a reaction is always a whole number and not 0 and never a fraction. Unlike order, remember in the previous section, the order of a chemical reaction can be any integer or even a fraction. It can even be 0, as we saw in zero order reactions. Whereas molecularity has to be necessarily a whole number but not 0, that is any number greater than 1. The value of molecularity of a simple or one-step reaction does not exceed 3, as we saw in the previous line that the probability that more than 3 molecules collide simultaneously to form a product is very small. Hence, molecularity greater than 3 is not observed in real life. Let us now solve a few examples from the lecture notes and understand questions based on order and molecularity. Let us solve example 1 from the lecture notes. The question is, in the chemical reaction, 2H2O2 forms 2H2O plus O2. The rate of formation of oxygen O2 is 36 grams per minute. Calculate subpart A, the rate of the reaction, subpart B, the rate of formation of H2O water, and subpart C, the rate of disappearance of hydrogen peroxide H2O2. Let us understand how to solve this question. Here it's given that the rate of formation of oxygen is 36 grams per minute. Let us express this in the terms of moles. We know that 1 mole of oxygen weighs 32 grams. So therefore, 36 grams of oxygen will weigh 36 by 32, which equals 1.125 moles. Therefore, the rate of formation of oxygen in terms of moles per minute is 1.125 moles per minute. Now in the first subpart, the question is find the rate of the reaction. We can either use the expression for rate of reaction based on stoichiometry or using the rate law of mass action. Here, we know the coefficients of the reactants and the products, and we also know the rate of formation of oxygen. So we can use the expression for rate of reaction based on stoichiometry. We know that rate of reaction based on stoichiometry in this case would be equal to minus 1 by 2 delta H2O2, which is the change in concentration of hydrogen peroxide, by delta T, which also equals plus 1 by 2 delta H2O by delta T, which is the change in the concentration of water, which equals plus 1 by 1 delta O2 by delta T. Here, the coefficients of H2O2, H2O and O2 in the reaction as seen are 2, 2 and 1. Now we know the rate of formation of oxygen, so we can use the rightmost expression, which is delta O2 by delta T. Let us substitute. When we substitute, we get the rate of the reaction equal to 1.125 moles per minute. In the second subpart, the question is find the rate of formation of H2. Now using the above rate of reaction expression, we can say that the rate of formation of H2, which is delta H2O by delta T, is 2 times delta O2 by delta T by transposing 2 in the denominator to the right hand side. Substituting, we get the rate of formation of water H2O will be equal to 2 multiplied by 1.125, which is 2.25 moles per minute. Hence, the rate of formation of water is 2.25 moles per minute. In the C subpart, the question is find the rate of disappearance of hydrogen peroxide H2O2. Again, using the expression for rate of reaction which we have obtained in subpart A based on stoichiometry, we can express the rate of disappearance of hydrogen peroxide, which is minus delta H2O2 by delta T, as minus delta H2O2 by delta T, which equals 2 times delta O2 by delta T. We know the rate of formation of oxygen is 1.125 moles per minute. So when we substitute the rate of formation of oxygen in this equation, we get the rate of disappearance of hydrogen peroxide H2O2 equals 2 times 1.125 divided by 1, which equals 2.25 moles per minute. Hence, the rate of the reaction is 1.125 moles per minute in the first subpart. The rate of formation of water is 2.25 moles per minute, which is the second subpart. And the rate of disappearance of H2O2 is 2.25 moles per minute. Let us solve example 2 from the lecture notes. The question is, calculate the overall order of a reaction which has a rate expression as follows. Subpart A, rate equals K, concentration of A raised to half, B, concentration of B raised to 3 by 2. Subpart B, rate equals K multiplied by concentration of reactant A raised to exponent 3 by 2 multiplied by concentration of B raised to minus 1. We know that the order of a reaction is equal to the sum of the powers of the concentration of the reactants in the rate law expression. Now in the first subpart, which is rate equals K multiplied by A raised to half, B raised to 3 by 2, the exponents are 1 by 2 and 3 by 2. So hence the order of this reaction will be the sum of these two exponents, which is 1 by 2 plus 3 by 2, which equals to 2. Hence it is a second order reaction, that is, the order is 2. In the second subpart, the rate is K, A raised to 3 by 2, B raised to minus 1. That is, the order of the reaction with respect to A is 3 by 2 and the order of the reaction with respect to B is minus 1. Again, the order is the sum of the exponents of the concentration of the reactant terms. Here, the order will be the sum of 3 by 2 and minus 1, which are the two exponents, which is 3 by 2 minus 1, which is half. Hence, in the second subpart, the reaction is a half order reaction. That is, the order of the reaction is equal to 1 by 2. Let us solve another question from the lecture notes. Question number 7. The question is, from the rate expression for the following reactions, determine the order of reaction and the units of the rate constants. Subpart A, 3NO in gaseous state forms N2O in gaseous state. The rate is given as K multiplied by concentration of nitric oxide NO whole square. Subpart B, H2O2 aqueous plus 3 I minus aqueous plus 2H plus forms 2H2O plus 3I minus. Here the rate is defined as K multiplied by concentration of H2O2 multiplied by concentration of I minus. In the first subpart, the rate is K NO whole square. That is, the exponent of the concentration term is 2. We know that the order is the sum of the exponents. Here, the exponent is 2, hence the order is 2. We can find the unit of the rate constant by performing dimensional analysis. Here, in this case, the unit of the rate constant will be concentration inverse time inverse. In the second subpart, the rate is defined as K multiplied by H2O2 raised to 1 multiplied by I minus raised to 1. Here the order of the reaction with respect to H2O2 is 1, as its exponent is 1, and the order of the reaction with with respect to the iodine ion, I minus, is also 1, as its exponent is also 1. We know that the order of a chemical reaction is the sum of the exponents of the concentration terms. Here, the exponents are 1 and 1. Hence, the order will be the addition of these two, which is 1 plus 1, that is equal to 2. Hence, it's a second order reaction. Again, we can find the unit of rate constant by performing dimension analysis, and here also the unit of the rate constant is concentration inverse multiplied by time inverse. Let us solve question number 10 from the lecture notes. The question is, the decomposition of ammonia NH3 on platinum surface is a zero order reaction. What are the rates of production of nitrogen N2 and hydrogen H2? If K, which is the rate constant, equals 2.5 multiplied by 10 raised to minus 4 mole inverse liters second inverse. Now here in the question, ammonia is decomposing to form nitrogen and hydrogen. Let's express this using a chemical reaction. On balancing, we can write the reaction as 2NH3 forms N2 plus 3H2. Let us now express the rate of the reaction based on stoichiometry. The rate of reaction will be equal to minus 1 by 2, where 2 is the stoichiometric coefficient of ammonia, multiplied by the rate of change of concentration of ammonia, that is delta NH3 by delta T, which equals 1 by 1. Here 1 is the coefficient of the N2, multiplied by rate of change of nitrogen concentration, which is delta N2 by delta T, which equals 1 by 3, as 3 is the stoichiometric coefficient of ammonia, of hydrogen, multiplied by rate of change of concentration of hydrogen, which is delta H2 by delta T. Now that we have expressed the rate of a reaction using stoichiometry, let us also use the rate of reaction based on rate law of mass action. Now here it's given that the reaction is a zero order reaction. Therefore, we know that the exponents of the concentration term in the rate equation will be 0. Hence, the rate of the reaction will be also equal to K using rate law of mass action. Now it's been given to us that the value of K equals 2.5 multiplied by 10 raised to minus 4 molars per second. Hence we can write that the rate is equal to 2.5 multiplied by 10 raised to minus 4 molars per second, which is the rate constant of the reaction. Let's now find the rate of production of nitrogen. Rate of production of nitrogen will be delta N2 by delta T, which, using the rate of reaction equation in the second step, is equal to K, which is equal to 2.5 into 10 raised to minus 4. Similarly, the rate of production of hydrogen, which is delta H2 by delta T, is 3 times K using the equation in the second step, which is 3 times 2.5 multiplied by 10 raised to minus 4, which is equal to 7.5 multiplied by 10 raised to minus 4 molars per second. Let us solve question number 12. In this question, it's given that a reaction is first order in A and second order in B. Subpart A, write the differential rate equation. Subpart B, how is the rate affected on increasing the concentration of B 3 times? Subpart C, how is the rate affected when the concentration of both A and B are doubled? In the first statement, it's given that the rate of the reaction is first order with respect to A and second order with respect to B. Hence, the exponent of the concentration of A in the rate equation will be 1, and the exponent of concentration of B in the rate equation will be 2. We can write rate equals K, concentration of A raised to 1, concentration of B whole square, which is the first subpart. In the second subpart, concentration of B is increased 3 times. So let us replace concentration of B in the rate equation by 3B. When we do that, we find that the rate of the reaction is now increased 9 times, as it is 9 multiplied by K multiplied by A multiplied by B square. In the C subpart, concentration of both A and B are double. So let us substitute 2a in place of a and 2b in place of b in the rate equation. We find that the rate is increased by 8 times in this case. Question number 14. Following results were obtained during the kinetic studies of the reaction 2a plus b forms C plus T. There's a table in which the observations of 4 experiments are given. We've been given the values of concentration of the reactants A and B and the initial rate of formation of the product T. The question is, determine the rate law and the order of the reaction. Now here 4 experiments are given and the concentrations of the reactants A and B are given. We can express the rate law using the rate law of mass action as follows. Using the first expression, we can write the rate of the reaction 6 multiplied by 10 raised to minus 3 equals K, which is the rate constant, multiplied by concentration of reactant A, which is 0.1 raised to X, concentration of reactant B, which is also 0.1 raised to Y. Let us name this equation as equation 1. We have considered X to be the order of reaction with respect to A and Y to be the order of reaction with respect to B. Let us derive 3 more equations based on the other 3 experiments. Using the experiment 2, we get the equation for rate of the reaction as 7.2 multiplied by 10 raised to minus 2 equals K, which is the rate constant, multiplied by 0.3 raised to X multiplied by 0.2 raised to Y. Using experiment 3, we get another expression for rate of the reaction. 2.88 multiplied by 10 raised to minus 1 equals K multiplied by 0.3 raised to X multiplied by 0.4 raised to Y. Using experiment 4, we get 2.4 multiplied by 10 raised to minus 2 equals K multiplied by 0.4 raised to X multiplied by 0.1 raised to Y. Let us name each of these 4 equations as 1, 2, 3 and 4 respectively. Now we have to first express its rate law, that is, we need to find the value of X and Y. To find the value of X and Y, we'll divide the 4th equation and the 1st equation and 3rd equation and the 2nd equation. Let us divide equation 4 by equation 1. When we divide, we get on the left hand side 2.4 multiplied by 10 raised to minus 2 divided by 6 multiplied by 10 raised to minus 3, which equals 0.4 raised to X multiplied by 0.1 raised to Y divided by 0.1 raised to X multiplied by 0.1 raised to Y. 0.1 raised to Y on the right hand side gets cancelled. We get 4 raised to 1 equals 4 raised to X. This is only true when X equals to 1. Hence we can say that the order of the reaction with respect to A, which was X, is equal to 1. Let us now find Y. To find Y, we'll divide equation 3 by equation 2. When we do so, we get on the left hand side 2.88 multiplied by 10 raised to minus 1 divided by 7.2 multiplied by 10 raised to minus 2, which equals 0.3 raised to X multiplied by 0.4 raised to Y divided by 0.3 raised to X multiplied by 0.2 raised to Y. 0.3 raised to X gets cancelled and we are left with 4 equals 2 raised to Y, hence Y equals to 2. Therefore, the rate order of the reaction with respect to the reactant B is 2. Hence, X is 1 and Y is 2. When we substitute these values of X and Y in the rate law, we get the rate law equals to concentration of A raised to 1, which is X, multiplied by concentration of B raised to 2, which is Y. Also, the order of the reaction is the sum of these two exponents, which is 1 plus 2, that is equal to 3. Hence, it's a third order reaction. In the same question, that is question 14, let us now determine the value of the rate constant K. We saw in the previous slide that the order of the reaction is 3. With respect to A, the order of reaction was 1, and with respect to B, the order of reaction is 2. The rate law is K, A raised to 1, B raised to 2. Now let us find the value of the rate constant here. Remember, there are 4 experiments given to us. In each of these experiments, we have been provided the values of the concentrations of the reactants A and B and the initial rate of formation of the product D. We will find the value of the rate constant individually using each of these 4 experiments. Hence, we can verify whether the value of the rate constant is correct or not. Let us solve using the values given in experiment 1. In experiment 1, using the rate law of mass action, we can state that the rate of the reaction is K, A raised to x, B raised to y. We found the value of x is 1 and the value of y is 2 in the previous slide. Substituting the values of the concentrations of the reactants A and B, we get rate equals K, which is the rate constant, multiplied by 0.1, which is the concentration of the reactant A, raised to 1, which is the order of the reaction with respect to the reactant A, multiplied by 0.1, which is the concentration of reactant B, raised to 2, which is the rate of the reaction with respect to B. Substituting the value of the rate of the reaction, which is 6 into 10 raised to minus 3, we get 6 multiplied by 10 raised to minus 3 equals K multiplied by 0.1 multiplied by 0.1 whole square. Solving this, we can find the value of K. We get K equals to 6 multiplied by 10 raised to minus 3 divided by 0.01, which is equal to 6. Hence, the value of rate constant is equal to 6. Let us now obtain the same value of rate constant using the other 3 experiments. Using experiment 2, we can say rate equals K multiplied by 0.3 raised to 1 multiplied by 0.2 raised to 2. Here 0.3 is the concentration of reactant A and 0.2 is the concentration of reactant B. Substituting for the value of the formation of D in place of the rate of the reaction, which is 7.2 into 10 raised to minus 2, in experiment 2, we get the value of K equals to 7.2 multiplied by 10 raised to minus 2 divided by 0.3 multiplied by 0.2, which is again equal to 6. The units of the rate constant is liter square per mole square per minute. We can verify this by performing dimensional analysis on the rate law. Let's use experiment 3 to find the value of rate constant. Using experiment 3, we can state that rate is equal to K multiplied by 0.3 raised to 1 multiplied by 0.4 raised to 2. The rate of the reaction in this case is 2.88 multiplied by 10 raised to minus 1. When we substitute, we get the value of the rate constant K equals 2.88 multiplied by 10 raised to minus 1 divided by 0.3 multiplied by 0.4, which equals to 6. Let us use experiment 4. We get rate equals K multiplied by 0.4 raised to 1 multiplied by 0.1 raised to 2. The value of K is then 2.4 multiplied by 10 raised to minus 1, which is the rate of the reaction in this case, divided by 0.4 multiplied by 0.1. Solving this, we get the value of K from experiment 4 as equal to 6. Hence, the value of the rate constant is 6 using any of the 4 experiments. Your assignment for today's session is given below. Do ensure you complete your assignment before we start with our next session.